In this video, we're going to talk about work, energy, and power. What is work? What is energy? And what is power? And how do these three things relate to each other? Well, let's begin our discussion with work. Work is something that is accomplished by the action of a force. So let's say you have this block that's resting on this horizontal surface. And let's apply a force. When this force acts on the block and moves it by some displacement d, that force is going to do work on this object. The work accomplished by the force is the product of the magnitude of the force times its displacement. Now sometimes these two vectors may not always be parallel to each other. So let's say if you're pulling the block with a tension force to the right at some angle, but the block is moving along the x direction. So the displacement vector will also be along the x direction. In this case, the work accomplished by that tension force is going to be the product of the tension force times the displacement times cosine of the angle between those two vectors. Now let's talk about energy. An object with energy has the ability to do work. Anytime a force acts on an object, what's really happening is that the force is transferring energy to the object. But before we get into that discussion, let's talk about two different forms of energy that you'll typically encounter in physics. The first one is kinetic energy. So what is kinetic energy? If you think about the word kinetic carries the idea of motion. So kinetic energy is present whenever you have an object in motion. So let's say if you have a ball that's moving, that ball has kinetic energy. Potential energy is basically stored energy. So let's say if you have a block that is above ground level, that block has potential energy. It has the ability to fall. And when it falls, it can do work. So any object that has energy has the ability to do work. To calculate kinetic energy, it's equal to 1/2 mv squared, where m is the mass in kilograms and v is the speed in meters per second. When using these units, you're going to get the kinetic energy in joules. Now potential energy, which is a type of stored energy, but this one is particularly gravitational potential energy, since this block has the ability to fall under the influence of gravity. Gravitational potential energy is equal to mgh. It's the mass in kilograms times the gravitational acceleration, which is in meters per second squared, times the height, which is in meters. And this will give us the gravitational potential energy in joules. Now, some textbooks will use the formula U for potential energy. And you might see like a subscript G, which indicates gravitational potential energy. So you might see the formula like this in your textbook. As for me, sometimes I use PE. This is a habit. PE, potential energy. I mean, it makes sense. So just be aware that you might see these two variables, which correlates to potential energy. But sometimes it's better to use this one because there are different types of potential energy out there. You have gravitational potential energy. You have elastic potential energy when you're dealing with springs. There's also electric potential energy, chemical potential energy. So there's a lot of different types, and this might be very useful when you have to distinguish between those different types of energy. Now, let's say if you have a ball that is moving, so because it's in motion, it has kinetic energy. And imagine a block being that's placed on this surface and the block is at rest. And let's say there's no friction on this horizontal surface. So this ball has kinetic energy, and this block doesn't have any kinetic energy, nor does it have potential energy. What's going to happen when the ball strikes the block? So let me draw another picture. So when the ball collides with the block, what's going to happen in terms of the forces that are acting on these two? Now, based on Newton's third law, we know that for every action force, or let me say this again, for every action, there is an equal and opposite reaction force. When the ball strikes the block, it's going to exert a force on a block. We can call that the action force. And anytime an object exerts a force on another object, the first object is doing work on the second object. The first one is exerting a force on the second one. Now at the same time, the second object is going to do work on the first object. The second object is going to exert an equal but opposite reaction force. And anytime you have a force acting on an object, there's going to be a transfer of energy. Each force is going to do work on the object that it's acting on. Now, the net work acting on an object is equal to the change in the kinetic energy of the object. This is basically the work energy theorem. Whenever a force increases the kinetic energy of the object, that force is doing positive work on the object. It's causing the object to speed up. Whenever a force decreases the kinetic energy of the object, it's doing a negative work on the object. So in this case, the ball, object number 1, it's exerting a force on block 2. It's causing block 2 to speed up. So the ball is going to do positive work on the object. It's transferring some of its kinetic energy to the block, object 2. Now while that's happening, block 2 exerts a reaction force on ball 1. As that is happening, block 2 is slowing down ball 1. And so block 2, it's doing negative work on the ball because it's slowing down. It's decreasing the ball's kinetic energy. And so when these two objects collide, there's a transfer of energy. The ball is transferring some of its kinetic energy to the block. And so this ball slows down, whereas at this block, it speeds up. Another way to determine whether or not a force does positive or negative work on an object is to consider the direction of the force and displacement vectors. When the force and displacement vectors, if they're parallel to each other, if they're pointing in the same direction, the work done by the force on the object is positive. Now, if the force and the displacement vectors are going in the opposite directions, let's say if they're 180 degrees from each other, then the work done is negative. Cosine of 180 is -1. When they're going in the same direction, the angle between them is 0. Cosine of 0 is 1. Now what about when the force and displacement vectors, when they're perpendicular from each other? What can you say about the work done? Let's say there's a 90-degree angle. Well, keep in mind the work done by a force is Fd cosine theta. So in this case, the angle is 90. Cosine 90 is 0. So anytime the force and the displacement vectors, if they're at right angles with each other, then the force does no work on the object. It simply causes the object to turn. So the force will become, basically, it's going to behave like a centripetal force, causing the object to turn into a circle. Now let's analyze what we have here. during the collision, if we focus on the block, we have an action force that is acting on the block and it's pointing to the right. And during the collision, the block is going to move to the right as well. So the force and the displacement vectors, they're in the same direction. So the action force is doing positive work on the block. Now let's focus on the ball during the collision. The ball is moving to the right, so its displacement is in the positive x direction. The reaction force, the force that block 2 exerts on ball 1, that reaction force is directed to the left. So because these two vectors are going in opposite directions, the work done by the reaction force is negative. So the reaction force is slowing down ball 1, and the action force is speeding up block 2. Now consider two situations. In the first situation, let's call this ball 1. Ball 1 was thrown into the air. It's going up. In the second situation, we have ball 2. Ball 2 is falling down under the influence of gravity. Now for these two situations, is the force of gravity doing positive work or negative work? What would you say? Well, let's focus on the first one. Gravity is a downward force. Gravity likes to bring things down to the ground. So based on this picture, the force of gravity will be in the negative y direction. Now, because the ball is moving upward, the displacement vector is going to be pointing upward as well. Now, since these two vectors are going in the opposite direction, we could say that the force of gravity is doing negative work on this ball while it's going up. Now, what about ball 2? Well, gravitational force will always be in the downward direction, and this time the ball is going down, so its displacement vector is also in the negative y direction. And we know that work is force times displacement, so when you multiply two negative values, you're going to get a positive answer. So the work done by gravity, whenever an object is falling, that work will be positive. Now, let's think about this in terms of kinetic energy. When the ball is going in the upward direction, the ball is slowing down. It's going to go up, eventually it's going to be at rest, and then it's going to fall back down. So while it's going up, the speed is decreasing. If the speed is decreasing, what can you say about the kinetic energy? Is the kinetic energy increasing or decreasing? If the speed is decreasing, the kinetic energy is decreasing. The kinetic energy is directly proportional to the square of the speed. So whenever an object speeds up, the kinetic energy increases. If it slows down, the kinetic energy decreases. Now, if the kinetic energy is decreasing, then the change in kinetic energy must be negative. And according to the work energy theorem, the net work acting on an object is equal to the change in the kinetic energy of that object. So if delta KE is negative, then the work will also be negative. So that's how we can determine the sign of the net work on the object. So that since gravity is the only force acting on the object, we can say that gravity is doing negative work on this object. Now let's focus on ball 2. Is ball 2 speeding up or slowing down? And how do you know? Notice that the force and the velocity vectors are in the same direction. When those two are in the same direction, the object is going to speed up. In the first example, the force and the velocity vectors are in opposite directions, so the object slows down. This object is experiencing, you could say, negative acceleration. It's moving up, but the acceleration, which is always in the direction of the net force, they're opposite to each other. When I mean opposite, the acceleration is opposite to the velocity vector, but the acceleration is always parallel to the net force. So since the acceleration is in the negative y direction and the velocity is in the positive y direction, the object is slowing down. It's experiencing deceleration. But for ball 2, it's speeding up. The force and therefore the acceleration is in the same direction as the velocity vector. So if it's speeding up, we know that the kinetic energy of ball 2 is increasing. Therefore, the change in kinetic energy for ball 2 will be positive. If the change is positive, then the work done on ball 2 is positive. So we could say that gravity is doing positive work on ball 2. It's speeding the ball up. And for ball 1, gravity does negative work on it because gravity is slowing it down. It's decreasing its kinetic energy. Now what about potential energy? Gravitational potential energy depends on the object's position relative to some reference point. So basically it depends on the height of the object as well as its mass. Now ball 1 is moving up. It's moving away from the ground. As it does so, the height between ball 1 and the ground increases. Therefore, the potential energy of ball 1 is increasing as it moves away from the ground. Ball 2 is moving towards the ground. So the height difference between the ground and the position of ball 2 is decreasing. So the potential energy of ball 2 is decreasing. Now, these two are usually, not always, but usually inversely related. When one goes up, the other goes down. In the case of ball 1, as ball 1 goes up, its kinetic energy is being converted to potential energy. The kinetic energy is decreasing, the potential energy is increasing. In the case of ball 2, the potential energy is being converted into kinetic energy. As it falls, it's losing potential energy, but it's speeding up, it's gaining kinetic energy. Now the sum total of an object's kinetic and potential energy is the mechanical energy. Mechanical energy is conserved when the only forces acting on the object are conservative forces. Gravity is a conservative force. Here, gravity decreases the kinetic energy of the object, but here it increases it. Now, gravity is not the only type of conservative force that you need to be familiar with. There are other types of conservative forces. These include the elastic force associated with springs and the electric force. Interestingly, all these three types of forces have their own types of potential energy, like gravitational potential energy, elastic potential energy, or electric potential energy. Now, non-conservative forces, they do not conserve the mechanical energy of an object. Friction is a non-conservative force. Friction will always slow down an object. It will never speed it up. Air resistance is another type of non-conservative force. And then push and pull actions, those type of forces, let's say if you're trying to push an object, that doesn't conserve the mechanical energy. And that can increase or decrease the mechanical energy. Another one is the tension force. That's a non-conservative action force. For instance, let's say if you have an object that is above ground level and you apply an action force that is greater than the gravitational force that's pulling it down. Let's say the action force that you're applying is significantly greater than the gravitational force. That means that there's going to be a net force pushing this object up. Now notice what's happening here. Because we have a net force, there is a net acceleration in the y direction, which means the object is speeding up in the y direction. So it's moving upward, and because there's an acceleration, it's speeding up. Therefore, the kinetic energy is increasing. Now, because you're moving it away from ground, you're increasing the height of the object at the same time. Therefore, the potential energy is increasing. So in this scenario, you're increasing both the kinetic and the potential energy. In the last scenario, one of these went up, the other went down. In this scenario, both of these forms of energies are going up. Now, mechanical energy, which is the sum of these two, kinetic and potential, is also increasing. Because if the kinetic and the potential energy is increasing, then the mechanical energy is increasing. So in this case, the mechanical energy is not conserved. You're using an action force to not only speed up the object to increase its kinetic energy, but you're also increasing its stored gravitational potential energy as you move it away from ground level. So you're increasing the object's mechanical energy. Therefore, this action force is a non-conservative force. Mechanical energy is not conserved when an action force is acting upon an object. So the work done by this action force is positive because the object's kinetic energy is increasing. Also, this force is in the same direction as the object's displacement. So that force is doing positive work on the object. Now this object has multiple forces acting on it, and each force does its own type of work on this object. The action force is clearly doing positive work on the object. Gravity is doing negative work on the object. As you can see, the force of gravity and the displacement vector are in opposite directions. Now what about the net work on the object? Is it positive or negative? Well, the net force is in the positive y direction, and it's in the same direction as the displacement vector, so the net work done on this object is positive. It's based on the direction of these two vectors. Now let's talk about power. What is power? Power is related to work, but power is a rate. It's the rate at which work is done on an object. It's also the rate at which energy is transferred from one object to another. Power, which we'll use the symbol P, power is equal to work divided by time. So an object that can do work in a short amount of time is exerting a lot of power. So power is the rate at which energy flows. Work is typically in units of joules. Time is usually in seconds. And power is usually in watts. 1 watt is equal to 1 joule per second. A kilowatt is equal to 1,000 watts. A megawatt is basically a million watts, 1 times 10 to the 6 watts. And a horsepower is 746 watts. So those are some units that you want to be familiar with. So remember, power is work over time, and it's the rate at which energy is being transferred. Another equation for power is force times velocity. If you know the force acting on an object, and you know the object's velocity, you can also calculate the power. And we could derive that equation from this one. Work, we know that work is force times displacement. And time is just t. Now, displacement over time, that's equal to velocity. So we can replace d over t with v. So we get power is force times velocity. So that's another way in which you can calculate the power being exerted. Now let's use another way to illustrate the concept of power. So let's say we have two individuals. We'll call this person John and this one Jared. Let's say that John lifts a 100 Newton box a distance of 1 meter above the ground. So work is force times displacement. So a force of 100 newtons times a displacement of 1 meter, he's doing 100 joules of work. Now let's say Jared does the same amount of work. He also lifts a 100 Newton box 1 meter above the ground. So he's doing 100 joules of work. But now let's say that John, he takes 1 second to lift up that box. But let's say Jared, it takes him 10 seconds to get the job done. Which individual exerts more power? Would you say it's John or Jared? Well, we know that power is work over time. It took John 1 second to get the job done. So the amount of power that he exerted is 100 watts. It's 100 joules per 1 second. So he's exerting a power of 100 joules every second. Now Jared, it took him 10 seconds to get the job done. So if we take his work divided by his time, it's 100 joules per 10 seconds, or 10 watts. So John, he transfers 100 joules in 1 second. Jared, he's only transferring 10 joules per 1 second. So we could say that John is more powerful. It took him a shorter amount of time to get the same job done, whereas Jared, it takes him a longer amount of time to get the job done. In 1 second, John can transfer 100 joules of energy. In 1 second, Jared can only transfer 10 joules of energy. So in this way, you could see two different ways in which you can view power. Power, the more power you have, the faster you can get the job done. The less power you have, the longer it's going to take you to get the same amount of work done. So you can think of power as work over time, or the rate at which energy is transferred. John has a greater rate at transferring energy. In 1 second, he can transfer 100 joules of energy. Jared, his rate of energy transfer is much less. In 1 second, he can only transfer 10 joules of energy. So hopefully this illustration helps you to understand the concept of power as being the rate at which energy is transferred. Now let's work on some practice problems. Number 1. What is the kinetic energy of a 5 kilogram block sliding across a frictionless horizontal surface at 12 meters per second? So let's begin with a picture. Okay, that line is not very horizontal. Let's draw a better one. So here is our 5 kilogram block, and it's moving horizontally at a speed of 12 meters per second. To calculate the kinetic energy, we can use this formula. Ke is equal to 1/2 mv squared. So the mass of the block is 5 kilograms, and the speed is 12 meters per second. 12 squared, or 12 times 12, that's 144. Half of 144 is 72. So it's 72 times 5. 7 times 5 is 35. So 70 times 5 is 350. And 2 times 5 is 10. So when you add 350 and 10, you get 360. So this block has 360 joules of kinetic energy. And that's the answer for part A. Number 2. What happens to an object's kinetic energy if the mass is doubled? Let's start with the equation. Ke is equal to 1/2 mv squared. For these types of problems, what you need to do is replace everything that doesn't change or that remains constant with a 1. And then what changes, plug in the appropriate number. So 1/2, I mean, that's a constant. We're just going to replace it with a 1. The mass, it doubles. We're going to replace it with a 2. The speed doesn't change, so we're going to plug in a 1. And this will give us 2. What this tells us is that if you double the mass, the object's kinetic energy will double. Now, if we move on to part B, what's going to happen to the speed? What's going to happen to the kinetic energy if we double the speed? So 1/2 doesn't change. We're going to replace it with a 1. The mass doesn't change, but this time we're doubling the speed. 2 squared is 4. So if you double the speed, the object's kinetic energy will increase by a factor of 4. Now what if you triple the speed? 3 squared is 9. The object's kinetic energy will increase by a factor of 9. Now what about part D? What if we triple the mass and we quadruple the speed? So we're going to replace m with 3, v with 4. 4 squared is 16. 3 times 16 is 48. So in this case, the object's kinetic energy will increase by a factor of 48. Number 3. What is the gravitational potential energy of a 2.5 kilogram book that is 10 meters above the ground? So let's draw a picture. So here is the 2.5 kilogram book. And it's 10 meters above ground level, so it has the ability to fall. How can we calculate the gravitational potential energy? The gravitational potential energy is going to be equal to mgh. So the mass is 2.5 kilograms. The gravitational acceleration is 9.8 meters per second squared. And the height is 10 meters. 2.5 times 9.8 times 10. So this is equal to 245 joules. So that's the gravitational potential energy of this book when it's 10 meters above the ground. A 10 kilogram ball falls from a height of 100 meters. Calculate the vertical speed of the ball during the first 4 seconds. So let's say this is the ground level, and here's a ball, and it falls down, and it's 100 meters above ground level. How can we calculate the vertical speed of the ball during the first 4 seconds? So I'm going to make a table. I'm going to put time, vertical speed, Vy, after that we need to calculate the height of the ball, and then the kinetic energy, potential energy, and finally the mechanical energy. So at t equals 0, the vertical speed of the ball is 0 because it's released from rest. Now, based on this equation, V final is equal to V initial plus AT. Now the initial speed we said it's 0. So the final speed in the y direction is the acceleration, which the acceleration in the y direction is gravitational acceleration times t. So every second, the vertical speed is going to increase by 9.8 meters per second. So at t equals 1, it's going to be 9.8 times 1, or simply 9.8. At t equals 2, it's going to be 9.8 times 2, so it's 19.6 meters per second. And at t equals 3, it's 9.8 times 3, so that's 29.4 meters per second. And 4 times 9.8 is 39.2. So as you can see, each second, the vertical speed increases by 9.8, which is the gravitational acceleration. Acceleration tells you how much the speed is going to change every second. Now what about the height? So at t equals 0, the ball is 100 meters above the ground. What is it going to be 1 second later? What equation can help us to find the distance that the ball travels? We could use this equation. Displacement is equal to v initial t plus 1/2 at squared. Now the initial speed in the y direction is 0, so this term is 0. So therefore the displacement in the y direction is 1/2 gt squared, because acceleration in the y direction is g. So it's going to be 0.5 times negative 9.8 times a time of just 1 second. So 1 squared. That's negative 4.9. So what that means is that the ball fell down a distance of 4.9 meters. So if it goes down 4.9 meters, 100 minus 4.9 is 95.1. It means that it's 95.1 meters above the ground. So 2 seconds later, that's going to be 0.5. You can use positive 9.8 if you want, as long as you understand what's happening. 0.5 times 9.8 times 2 squared, that's 19.6. So it fell down by 19.6. If you use negative 9.8, it will be negative 19.6. The negative sign simply tells you that it falls down by 19.6 meters. Now, if you're looking for the velocity as opposed to the speed, these will all be negative values. So when you use the equation, v final is equal to gt. G is negative, so this will give you velocity. But we don't really need velocity in this problem because kinetic energy is based on speed. So that's why I chose to use positive values. But if you're dealing with velocity, because the ball's going in a negative y direction, these values should have negative velocity values. However, since speed is positive, we don't have to worry about that. So now let's calculate the height 2 seconds later. So if the displacement is negative 19.6, we need to subtract 19.6 from 100. So the height 2 seconds later is now 80.4 meters. What about 3 seconds later? So dy is going to be 1/2 negative 9.8 times 3 squared. So that's negative 4.9 times 3 squared. And so that's a displacement of negative 44.1. So let's subtract that from 100. And so we're going to have a height of 55.9 meters. Now let's do the same thing for a time of 4 seconds. So negative 4.9 times 4 squared is negative 78.4 meters. So 100 minus 78.4 is 21.6 meters. So that's the height above the ground 4 seconds later. Now let's calculate the kinetic energy of this ball for each second. Now at t equals 0, because the speed is 0, the kinetic energy will be 0. 1 second later, it's going to be 1/2 times a mass of 10 times v squared, which is 9.8 squared. So half of 10 is 5, so 5 times 9.8 squared, that's going to give us an energy of 480.2. Now let's repeat the process. So the next one's going to be 1/2 times 10, which is basically going to be 5. The mass is not going to change. So 5 times 19.6 squared. So that's 1,920.8. And then 5 times 29.4 squared. That's 4,321.8. And then 5 times 39.2 squared. That's 7,683.2. Now let's move on to the next column. let's calculate the potential energy at the different times. So potential energy is mgh. So it's based on the height. So the mass is always going to be 10, g is 9.8, and the height is the stuff that's going to change. So initially the height is 100. So it's going to be 98 times the height. So 98 times 100 is 9,800 joules of energy. Now what about when the height is 95.1? So the 98 part is going to stay the same, and then the height is just 95.1. So 98 times 95.1 is 9,319.8. Next is going to be 98 times 80.4, and so that's 7,879.2. I'm dealing with some very small spaces. I should have made this larger. So next is 98 times 55.9, which is 5,478.2. And then finally, 98 times 21.6, which is 2,116.8. So now what I'm going to do is calculate the total mechanical energy. The mechanical energy of a system is the sum of the kinetic energies and the potential energies. So for the first one, it's 0 plus 9,800. So that's going to be 9,800. Next, if we add these two values, so 480.2 plus 9319.8, you get the same answer, 9,800. And then if we add those two values, so 1920.8 plus 7879.2, you still get 9,800. And then 4321.8 plus 5478.2, and I think you see the picture. Now, just to make sure everything is correct, I'm going to add the last one as well. Make sure I didn't miss anything. So what does this all mean? What can we learn from this? So we see that the total mechanical energy is conserved. It's a constant value, it doesn't change. It remains 9,800 joules. So what's happening is that as the ball falls, the potential energy is being converted to kinetic energy. Notice that the potential energy decreases from 9,800 to 2116.8. Once it hits the ground, the potential energy will be 0. And while it's falling, the kinetic energy increases. The object is falling down with greater speed. The speed is increasing. And so as the potential energy decreases, the kinetic energy increases, allowing the mechanical energy to remain constant. Now what about the last part? Is gravity a conservative force? It turns out it is. The only force acting on the ball is the gravitational force. Whenever you have a system in which only conservative forces are acting on the system, the total mechanical energy will be conserved. If you have a non-conservative force like friction, friction will decrease the mechanical energy of the system. Eventually, the object will come to a stop. If you roll a ball on a carpet, the ball will eventually come to a stop because friction is going to slow it down to a stop. And so friction reduces the mechanical energy of a system. Now, let's say if you apply a force to accelerate the object, you can increase its overall mechanical energy. So an applied force or frictional force, these are both non-conservative forces. They can increase or decrease the mechanical energy of a system. But gravity it's a conservative force. It doesn't change the mechanical energy of a system. So that's why the mechanical energy is constant, because we only have a conservative force acting on the ball. So this problem says that a 70 Newton force is applied horizontally to a 10 kilogram block at rest for a displacement of 200 meters across a frictionless surface. So this is going to be the horizontal frictionless surface, and this is the 10 kilogram block. So we're going to apply a force of 70 newtons. Now, the block is going to travel for a displacement of 200 meters. So the force is going to be applied until the block travels a distance of 200 meters. During that time, we want to calculate how much work is done by the force as it travels from point A to point B. So the work done by the force is the force times the displacement. So the force is 70 newtons and the displacement is 200 meters. So it's 70 times 200. 7 times 2 is 14, so we just got to add the 3 zeros. So the work done by the force is 14,000 joules. Now, this force is the only force acting on the block in the x direction. So this force represents the net force as well. So we could say that this is also the net work done on the block because there's no other forces acting on it in the x direction. So this is the answer to part A. Now we could set the net work equal to the change in kinetic energy. So that is the final kinetic energy minus the initial kinetic energy. Now at point A, the block is at rest, which means it's not moving. The speed of the block is 0. And if the speed is 0, the kinetic energy is 0. So the initial kinetic energy is 0, which means the net work is equal to the final kinetic energy, which is 14,000 joules. So part A and part B is the same. It's both 14,000 joules. So now we can move on to part C. The final kinetic energy is equal to 1/2 mv squared. And the final kinetic energy is 14,000. And the mass is 10. So we can calculate the final speed. Half of 10 is 5. And so I'm going to take 14,000 and divide it by 5. And so that's equal to 2,800. So 2,800 is equal to the square of the final speed. So if we take the square root of both sides, this will give us the final speed. So the final speed at part B, not part B, but point B, rather, which is the square root of 2,800, that's 52.9 meters per second. So that's the answer to part C. Now let's move on to part D. What is the acceleration of the block in the horizontal direction? Well, we know that the net force is equal to this force because that's the only force in the x direction. And the net force in the x direction is the mass times the acceleration in the x direction, according to Newton's second law. So F equals ma. Now, we have a mass of 10, and the force applied is 70 newtons. So the acceleration is going to be 70 divided by 10, which is 7 meters per second squared. So now that we have the acceleration, let's move on to part E. Use kinematics to calculate the final speed of the block. Let's confirm the answer that we have. What kinematic formula do you know can help us to calculate that final speed? So we have the acceleration, we know the initial speed is 0, and we have the displacement. So the equation that has the initial speed, final speed, acceleration, and displacement is this equation. V final squared is equal to V initial squared plus 2AD. The initial speed is 0. The acceleration is 7. And the displacement is 200. So 2 times 7 is 14. And 14 times 200, well, 14 times 2 is 28. So 14 times 200 is 2,800. So we can see that this is going to lead us to the same answer. If we take the square root of 2,800, that's going to be 52.9 meters per second. So as you can see, there's multiple ways in which you can find the final speed of the block. You could use kinematics, or you could use the work energy principle. In fact, if you combine the two methods, you can derive the equation for the kinetic energy of an object. So we know that the net work is equal to the change in kinetic energy. But to prove that, the net work also equals to the force times the displacement. And force is mass times acceleration. Now, using this equation, V final squared is equal to V initial squared plus 2AD. So I'm going to subtract both sides by V initial squared. So I have V final squared minus V initial squared is equal to 2AD. Next, multiply both sides by a half. So on the left side, I'm going to have 1/2 V final squared minus 1/2 V initial squared. And 1/2 of 2AD is simply A times D, because 1/2 times 2 is 1. So what I'm going to do now is I'm going to replace AD with this expression, because they equal each other. So the net work done on an object is going to be the mass times 1/2 V final squared minus 1/2 V initial squared. So if we distribute the mass, it's going to be 1/2 mv final squared minus 1/2 mv initial squared. And so this expression is the final kinetic energy, and this expression is the initial kinetic energy. So therefore, we could say that kinetic energy is 1/2 mv squared. And that's how you could derive the formula for kinetic energy, as you can see here. And so the final kinetic energy minus the initial kinetic energy is equal to the change in kinetic energy. So we have this principle, the work energy principle. That is, the net work done on an object is equal to the change in the kinetic energy of that object. So keep this principle in mind. It's very useful. How much work is required to accelerate a 1,500 kilogram car from 15 meters per second to 40 meters per second? So keep in mind the net work is equal to the change in the kinetic energy. So that's the final kinetic energy minus the initial kinetic energy. So it's 1/2 mv final squared minus 1/2 mv initial squared. Now, to make the calculation a lot easier, we can factor out 1/2 m because it's the GCF. So the net work is also equal to 1/2 m times v final squared minus v initial squared. So the mass of the car is 1,500 kilograms. The final speed is 40, and the initial speed is 15. So half of 1,500 is 750, and 40 squared is 1,600. 15 squared is 225. And 1,600 minus 225 is 1,375. So let's multiply 1,375 by 750. So you should get 1,031,250 joules. So that's the net work done on the car. Now let's move on to part B. What is the average net force acting on the car if it reaches a final speed of 40 meters per second while traveling a distance of 275 meters? So we know that the net work is equal to the net force times the displacement. Distance and displacement is the same if you have an object traveling in one direction, if it doesn't change direction. So we have the net work. It's about 1,000,000 joules. Our goal is to calculate the average net force. And the displacement is 275 meters. So all we got to do is take the work that we have and divide it by 275. So you should get an average net force of 3,750 newtons. So let's see if we can get this answer using another technique. The second way in which we could calculate the average net force is using kinematics. We need to find the acceleration first. So let's use this formula to calculate the acceleration. The final speed is 40, the initial speed is 15, and the displacement is 275. So we know 40 squared is 1600, 15 squared is 225, and 2 times 275 is 550. Now 1600 minus 225 is 1375. So to calculate the acceleration, we need to divide both sides by 550. 1375 divided by 550 is 2.5 meters per second squared. So that's the acceleration of the vehicle. So now we can calculate the net force using Newton's second law. Net force is equal to ma. So the mass of the vehicle is 1,500 kilograms multiplied by an acceleration of 2.5 meters per second squared. So 1,500 times 2.5, as we expect, is 3,750 newtons. So the answer is confirmed. How much work is done by a constant 50 Newton force that acts over displacement of 10 meters? To find the work done by a constant force, it's simply the force times the displacement, assuming that they're both parallel to each other. So it's going to be 50 newtons times the displacement of 10, which is 500 joules. Now what about part B? How much work is done by a varying force that increases at a constant rate from 40 to 80 over displacement of 10? So if you have a force that's not constant, but it's changing at a constant rate, then the work done by that force is equal to the average force times the displacement. The average force is basically the initial force plus the final force divided by 2, multiplied by the displacement. So it's going to be 1/2 times the sum of the initial and the final force times the displacement of 10. 40 plus 80 is 120, and half of 120 is 60. So the average force is 60, which is between 40 and 80. So it's 60 times 10, which means it's 600 joules. Now you can confirm these answers graphically. In the case of the first example, let's make a graph. So I'm going to put the force vector on the y-axis and displacement on the x-axis. Now the force is a constant 50. So let's put 50 here. And the displacement is 10. So if you have a force displacement graph, the work done by this force is equal to the area under the curve. And so what we have is a rectangle. The area of a rectangle is length times width. So the length in this example is the force, the width is the displacement. So it's 50 times 10, and so the work done is 100, or rather 500 joules. Now for the second example, we can graph it as well. So this is going to be the force and the displacement vector. Now the force increases from 40 to 80 over a displacement of 10 meters. So at 0 the force is 40, and at 10 it's 80. so it increases at a constant rate. So what we need to do is find the area of the shaded region. How can we do so? For this type of graph, you want to split it into two parts, into a rectangle and a triangle. The area of the bottom rectangle is the length times the width, so it's 40 times 10, which is 400 joules. Now we need to calculate the area of the triangle, which is 1/2 base times height. The base of the triangle is 10 meters, and the height of the triangle is the difference between 80 and 40, which is 40. Now 10 times 40 is 400, and half of that is 200. So the total area under the curve is 200 plus 400, which gives you 600. So that's how you can calculate the work done by a varying force. You can use this equation if the force changes at a constant rate, or you could simply find the area under the curve.